The following is a review of the quantitative methods principles designed to address the learning outcomes statements set forth by the CFA Institute. It is also covered in the time value of money. When working with time value of money problems, it is imperative that you be able to use a financial calculator. There is simply no other way that you will have time to solve time value of money problems. I'd like to point out that CFA Institute allows only two types of calculators for the exam: the Texas Instrument BA2 Plus, including the professional, and the Hewlett-Packard HP12C, including the Platinum model. This reading is structured with the TI BA2 Plus in mind. So, if you do not already own a calculator, please go out and buy a TI BA2 Plus. However, if you already own the HP12C and you are comfortable with it, by all means continue to use it. I'd like to draw your attention to the streaming video called Calculator Basics that is available to all Schweizer Study Notes purchasers on our website, schweizer.com. This video contains detailed information with many illustrations on how to set up your calculator, handle multiple payment periods, and how to deal with various types of time value of money calculations. So, if you're even the least bit uncertain about how to use your calculator, you'd be well advised to access this information and view this video. A useful tool when working with time value of money problems is a timeline. A timeline is a diagram of the cash flows associated with a time value of money problem. A timeline is a horizontal line starting with the value 0 and divided into equal segments through the end of the last period in the time value of money problem. I want to stress here that the numbers on a timeline represent ends of the periods. This means that the cash flow that appears below the number 2 on a timeline represents a cash flow that occurs at the end of period 2. Keep in mind, when working time value of money problems using timelines, that a cash flow that occurs at the end of a given period is equivalent to a cash flow that occurs at the beginning of the next period. For example, a cash flow that occurs at the end of period 2 is equivalent to a cash flow that occurs at the beginning of period 3. I encourage you to get in the habit of drawing timelines prior to starting a time value of money problem. Timelines will help you visualize the cash flows associated with the time value of money application and can save you a lot of time and help you avoid mistakes when working time value of money problems. Okay, let's get started. The first LOS is to interpret interest rates as required rates of return, discount rates, or opportunity costs. Interest rates are our measure of the time value of money. Although risk differences in financial securities lead to differences in their equilibrium interest rates. Equilibrium interest rates are the required rate of return for a particular investment, in the sense that the market rate of return is the return that investors and savers require to get them to willingly lend their funds. Interest rates are also referred to as discount rates, and in fact, the terms are often used interchangeably. If an individual can borrow funds at an interest rate of 10%, then that individual should discount payments to be made in the future at that rate in order to get their equivalent value in current dollars or other currency. Finally, we can also view interest rates as the opportunity cost of current consumption. If the market rate of interest on one-year securities is 5%, earning an additional 5% is the opportunity foregone when current consumption is chosen rather than saving or postponing consumption. The next LOS requires us to explain an interest rate as the sum of a real risk-free rate and premiums that compensate investors for bearing distinct types of risk. The real risk-free rate of interest is a theoretical rate on a single-period loan that has no expectation of inflation in it. When we speak of a real rate of return, we are referring to an investor's increase in purchasing power after adjusting for inflation. Since expected inflation in future periods is not zero, the rates we observe on T-bills, for example, are risk-free rates, but not real rates. T-bill rates are nominal risk-free rates because they contain an inflation premium. The approximate relation here is nominal risk-free rate equals the real risk-free rate plus the expected inflation rate. Securities may have one or more of several risks, and each added risk increases the required rate of return on the security. These types of risks are default risk, the risk that a borrower will not make the promised payments in a timely manner; liquidity risk, the risk of receiving less than fair value for an investment if it must be sold for cash quickly; and maturity risk, as we will cover in detail in the section on debt securities. The prices of longer-term bonds are more volatile than those of shorter-term bonds. Longer maturity bonds have more maturity risk than shorter-term bonds and require a greater maturity risk premium. Each of these risk factors is associated with a risk premium that we add to the nominal risk-free rate to adjust for greater default risk, less liquidity, and longer maturity relative to a very liquid, very short-term default risk-free rate, such as that on U.S. Treasury bills. The required interest rate on a security equals the nominal risk-free rate plus a default risk premium plus a liquidity premium plus a maturity risk premium. The next two LOS ask us to calculate and interpret the effective annual rate given the stated annual interest rate and the frequency of compounding, and to solve time value of money problems for different frequencies of compounding. Financial institutions typically quote rates as stated annual rates or nominal rates, along with a compounding frequency, as opposed to quoting rates as periodic rates, the rate of interest over a single compounding period. For example, the bank will quote a savings rate of 8% compounded quarterly rather than 2% per quarter. The rate of interest that the investors actually realize as a result of the compounding is known as the effective annual rate, or the EAR. EAR represents the annual rate of return actually being earned after adjustments have been made for different compounding periods. To compute the EAR, we use the formula EAR equals the quantity 1 plus the periodic rate raised to the number of compounding periods per year minus 1. Please note that the EAR for a stated rate of 8% compounded annually is not the same as the EAR for 8% compounded semi-annually or quarterly. Whenever compound interest is being used, the stated rate or the nominal rate and the actual rate or the effective rate of interest are equal only when the interest is compounded annually. In all other cases, EAR will be greater than the stated rate. So, when comparing investment alternatives, or borrowing rates that are expressed using different compounding periods, it is necessary to compute the EAR in order to have an apples-to-apples comparison. You must be able to calculate an effective annual rate given a stated rate of interest and a compounding frequency. To meet the requirements of this LOS, let's consider an example where we want to compute the EAR using a nominal rate of 12% compounded quarterly. In this case, the number of compounding periods per year is equal to 4, so the period rate is equal to the annual stated rate of 12 divided by 4, or 3%. Thus, the EAR is equal to 1 plus 0.03 raised to the fourth power, and then we take this quantity and subtract 1. This gives us 1.1255 minus 1, or 12.55%. Up to now, all of our TVM examples, or time value of money examples, have assumed annual compounding periods. When solving time value of money problems using your financial calculator, it is possible to adjust the P over Y key to correspond to the compounding frequency. For instance, if the compounding frequency is quarterly, you would set the P over Y key equal to 4. Then, when you entered an annual interest rate, your calculator would automatically convert this rate to a quarterly rate. We do not recommend this approach. Instead, keep your calculator set at all times with the compounding mode P over Y equal to 1. Then when you enter the payments per compounding period. When you enter the interest rate per compounding period, and for n, instead of years, just simply enter the number of compounding periods. Let's consider an example where we want to compute the future value of a single $2,000 cash flow at the end of 5 years using a nominal interest rate of 12% with quarterly compounding. To solve this problem, we enter the relevant data and compute future value. In this case, because we have quarterly compounding over 5 years, n is equal to 20 periods or 4 quarters per year times 5 years. The interest rate per quarter is the 12% annual rate divided by 4 quarters a year, or 3%. The present value is entered as negative $2,000, and we compute a future value of $3,612.22.